Beyond the orbit of Neptune, where sunlight is a dim and distant memory, there lies a ring of frozen debris so vast that it dwarfs the inner solar system. But here's the thing. We have never truly seen it up close. We have never sent a dedicated spacecraft to fly through its heart. And when we try to weigh it, to measure its bulk, we find something deeply unsettling. The Kuiper Belt, this passive, sprawling disk of ice and rock, is almost entirely empty. It is a ghost, a skeleton of what it once was. And the more we study it, the more we realize that what remains is stranger, more violent, and more terrifying than anyone ever predicted. You might think the Kuiper Belt is just a quiet, frozen warehouse of leftover comets, a cosmic attic filled with dusty relics from the birth of the solar system. But that image is dangerously wrong. The Kuiper Belt is not static. It is a dynamic engine of destruction, a place where orbits twist and warp, where entire worlds are torn apart and reassembled, and where the very structure of the belt is slowly unraveling. And if you look closely at the evidence, you'll start to see that the belt might be hiding something big, something that bends space and time around it, something that might be a planet. But I'm getting ahead of myself. Let's start at the beginning. The Kuiper Belt is not a far-off hypothesis. It is a real physical structure, and we have the receipts to prove it. In 1992, astronomers David Jewett and Jane Liu were staring at the sky with a telescope on Mauna Kea, looking for anything that moved. They were hunting for a faint speck of light that shifted against the background stars, the signature of an object beyond Neptune. For years, they found nothing. Their colleagues told them they were wasting time. The prevailing wisdom said that the region beyond Neptune was empty. The solar system ended at Pluto, but on August 30th, 1992, Jewett and Liu found it. A tiny dot, no brighter than a 23rd magnitude star, crawling across the sky at a snail's pace. They named it I2QB1, now called Albion. It was the first confirmed Kuiper Belt object beyond Pluto and its moon Charon. That discovery was a tectonic shift in our understanding. Suddenly, the solar system didn't end at Neptune. It kept going and going and going. Today, we have cataloged over 2,000 Kuiper Belt objects, and we estimate that the belt contains at least 70,000 objects larger than 100 kilometers in diameter. That's not a guess. That's a lower bound based on direct observation. The Kuiper Belt is real. It is massive in extent, and it is full of worlds. But here's the first terrifying reality. Most of that mass is missing. When astronomers run computer models of how the solar system formed, they predict that the region beyond Neptune should have accumulated between 20 and 50 Earth masses of material. The protoplanetary disk that surrounded the young sun was rich in ice and rock, and out in the cold depths, beyond the frost line, there should have been a dense swarm of planetesimals, building blocks that should have clumped together into planets. But when we actually measured the mass of the Kuiper Belt, we got a number that was shockingly small. The total mass of the belt today is only about 1/16 the mass of Earth. That's roughly 5 times the mass of our moon. Let that sink in. The models predicted 20 Earth masses. We found less than 1/10% of that. It's like walking into a bank vault that should hold $10 million and finding only a crumpled $5 bill on the floor. Where did all the money go? To understand this, you have to picture the early solar system as a chaotic construction zone. The giant planets, Jupiter, Saturn, Uranus, Neptune weren't born in their current orbits. They migrated. Neptune, in particular, is the prime suspect in the great missing mass mystery. In the first few million years after the solar system formed, Neptune slowly drifted outward, plowing through the icy debris disk like a cosmic bulldozer. It scattered objects in all directions, flinging some into the inner solar system, some into the distant Oort cloud, and some completely out of the solar system. Neptune's gravity acted as a giant gravitational slingshot, ejecting vast amounts of material into interstellar space. But that's not the only mechanism at work. Even today, the Kuiper Belt is slowly eating itself alive. Objects within the belt collide. They smash into each other at velocities that can exceed 1 kilometer per second. These impacts don't just chip off small pieces. They can shatter entire bodies, turning them into clouds of debris. Those fragments then collide with other fragments, creating a cascade of destruction that grinds the belt down into ever finer dust. And then, once the particles are small enough, they get swept away by the solar wind and by radiation pressure from the sun. The Kuiper Belt is a grinding mill, pulverizing itself into oblivion, grain by grain, year by year. If that sounds bleak, it gets worse. The rate of this collisional cascade is such that, over the next few billion years, the Kuiper Belt will continue to lose mass. By the time the Sun becomes a red giant, in about 5 billion years, the belt may have almost completely disappeared. What we see today, this vast ring of icy worlds, is only the shadow of its former glory. It is a cemetery of a once grand structure, a monument to violence and entropy. But wait, if the Kuiper Belt is eroding away, why does it still have any structure at all? Why isn't it just a scattered mess? The answer lies in the bizarre way its orbits are arranged. And this is where things start to get truly unsettling. In 2017, astronomers Catherine Volk and Renu Malhotra at the University of Arizona were studying the orbits of over 600 Kuiper Belt objects. They noticed something that shouldn't have been there. The plane of the Kuiper Belt, the imaginary flat disk around which most objects orbit, is warped. Up to a distance of about 50 astronomical units, or about 4.6 billion miles from the Sun, everything is normal. The belt lies flat, tilted only about 1.8 degrees relative to the ecliptic. But beyond that distance, between 50 and 80 astronomical units, the plane begins to tilt, and tilt, and tilt. At 80 astronomical units, it deviates by more than 9 degrees from the expected plane. That's not a small wobble. That's a massive systematic bend. The probability that this is a statistical fluke? About 1 to 2%. In science, that's basically a smoking gun. Something is physically pulling on the outer Kuiper Belt, bending its orbital plane over millions of years. The most likely explanation is a hidden planet, an object with a mass similar to Mars, orbiting at about 60 astronomical units, whose gravity has slowly tilted the entire structure. But it could also be the ghost of a close stellar encounter, a star that passed near our solar system in its infancy, warping the belts forever. Whatever the cause, the outer Kuiper Belt is not flat. It is a twisted, breathing structure, precessing with a period of 1.9 million years, as if the entire ring is slowly rocking back and forth. This warp is a direct clue to the hidden mass problem. If a Mars-sized planet is out there, it would explain not only the warp, but also some of the missing mass. Perhaps the missing material didn't all get ejected. Perhaps some of it coalesced into a hidden world, lurking in the darkness, waiting to be discovered. Astronomers have been hunting for this planet for years, They call it Planet 9, but it hasn't been found yet. And until it is, the warp remains a terrifying mystery, a gravitational anomaly that tells us the Kuiper Belt is not a simple static ring. It is being actively shaped by forces we cannot see. Now, let's zoom in on the individual objects within the belt, because the Kuiper Belt is not a uniform smear of icy rocks. It has distinct populations, and they are weirdly, unnervingly specific. The region between 42 and 45 astronomical units from the Sun is called the classical Kuiper Belt. And within that narrow slice of space, there are two completely different populations of objects living side by side. One is called the cold population. These objects have nearly circular orbits with inclinations less than 10 degrees. They move slowly, sedately, like old men walking in a park. The other is called the hot population. And before you ask, no, the words cold and hot don't refer to temperature. They refer to orbital speed, following an analogy from physics. When you heat a gas, its particles move faster and with more random directions. The hot population of the Kuiper Belt consists of objects with orbits inclined by as much as 30 degrees, some even more. They are tilted, chaotic, and energetic. Why do these two populations coexist in the same zone? The cold population probably formed in place at the same distance from the Sun and never got disturbed. The hot population, on the other hand, was likely scattered inward from farther out in the belt, stirred up by Neptune's migration. They are refugees from a more violent region, and they share the same space without mixing. It's as if you had a neighborhood where one street was calm and orderly, and the next street over was a riot, both existing in the same city block, separated by an invisible line. But the most bizarre fact about the Kuiper Belt involves its binary systems. Binary objects, two worlds that orbit each other, are extremely common in the belt. In the cold classical region, about 30% of objects are binaries. That's an astonishingly high fraction. But here's the twist. Those binaries exist in only two extreme configurations. Either they are super tight, almost touching, like two peas pressed together in a pod, or they are ultra-wide, separated by tens of thousands of miles, orbiting each other at speeds slower than a person walking. Intermediate separations are almost completely absent. This is not a statistical fluke. It is a signature of instability. Take the binary system 2001 QW3T2. Its two components are separated by about 65,000 miles, more than 8 times the diameter of Earth. They orbit each other at a glacial pace of just 6.7 miles per hour. That's 3 meters per second. A human can run faster than that. According to conventional dynamics, such a loose, slow-moving pair should be torn apart by the gravitational influence of passing stars or other Kuiper Belt objects in just a few million years. Yet 2001 QW322 has survived for billions of years. It is a fossil from the early solar system, a relic of a time when the belt was much denser and velocities were much lower. On the other end of the spectrum, we have contact binaries like Arokoth. Arokoth is two separate lobes that gently touch, fuse together at the slowest possible impact speed, about 2.2 miles per hour, or 1 meter per second. It is the most pristine object ever visited by a spacecraft, a snowman-shaped world that formed when two objects drifted together in a gentle cosmic kiss. But why are there so few binaries in between? Why don't we see pairs separated by, say, a few hundred miles? Simulations show that intermediate separations are dynamically unstable. They evolve inevitably toward one of the two extreme states. If two objects are moderately close, their mutual gravity and the tidal forces from the Sun and Neptune will either push them closer together until they merge into a contact binary, or pull them farther apart until they become an ultra-wide pair. There is no stable middle ground. The Kuiper Belt forces binaries to choose, either touch or drift. There is no in-between. It's like a cosmic relationship counselor that only allows two outcomes: total commitment or total distance. This binary instability is a direct consequence of the belt's low density and low relative velocities. In the early days, when the belt was thick with material, collisions were frequent and binaries could form in all shapes and sizes. But as the belt thinned out, the gravitational environment changed. The remaining binaries were slowly sculpted, pushed to the extremes. What we see today is not a random sample of what once existed. It is a survival of the fittest scenario, where only the most extreme configurations could persist. Now, let's talk about what happens when the Kuiper Belt interacts with the planets, because it does not just sit there quietly. It gives, it takes, and it leaves scars. The most dramatic example is Triton, the largest moon of Neptune. Triton is 1,680 miles in diameter, bigger than Pluto. It is the seventh largest moon in the solar system, and it orbits Neptune backward, while every other large moon orbits in the same direction as its planet's rotation, what we call prograde orbit. Triton goes the opposite way. That is a dead giveaway that Triton did not form around Neptune. It was captured. And captured from where? Almost certainly from the Kuiper Belt. Triton's density, its surface composition of nitrogen, methane, and carbon monoxide ices, its active geysers that shoot liquid nitrogen into the sky. All of it matches the properties of large Kuiper Belt objects like Pluto. Triton was a Kuiper Belt world that wandered too close to Neptune and got snared. It may have been part of a binary system, like Pluto and Charon, and the encounter with Neptune's gravity ripped that binary apart, capturing one member and flinging the other away. This capture event would have been catastrophic. Triton's orbit was initially wildly elliptical, and the tidal forces would have heated its interior, possibly melting its core and triggering the geological activity we see today. Triton is a refugee, a prisoner of war taken from the Kuiper Belt, but it's not alone. Saturn's moon Phoebe is also a captured Kuiper Belt object. Phoebe orbits Saturn backward, deep in the outer reaches of the moon system. The Cassini probe revealed that Phoebe is covered in water ice and dark organic materials, exactly what you'd expect from a KBO. And then, there are all the irregular satellites of Jupiter, Saturn, Uranus, and Neptune, tiny moons that orbit on tilted eccentric paths far from their parent planets. Most of them are probably captured Kuiper Belt objects. The giant planets have been raiding the belt for billions of years, snatching up frozen trophies and dragging them into orbit. In a very real sense, parts of the Kuiper Belt are scattered throughout the entire solar system. When you look at Triton, you are looking at a piece of the Kuiper Belt. When you see Phoebe in images from Cassini, you are seeing a KBO. The belt has bled into the inner solar system, leaving its marks on every planet beyond Mars. And this brings us to a question that haunts planetary scientists. Is the Kuiper Belt still alive today, or is it just a graveyard? On one hand, the belt is clearly eroding. Collisions between objects are rare now, but they still happen. Each collision grinds down a piece of the belt, producing fragments that become comets or dust that gets blown away. The total mass is decreasing, albeit slowly. In a few billion years, the belt may be truly dead, a static ring of debris that never changes. But to call it a graveyard would be to ignore the evidence of ongoing activity. Makemake, one of the largest KBOs, emits methane into space, suggesting seasonal sublimation and possibly cryovolcanism. Haumea has a ring system, a ring that defies classical physics, because the Roche limit should have prevented it from forming so close to the body. Quaoar shows signs of crystalline water ice on its surface, which can only exist if it has been recently refreshed by geological processes. These are not dead worlds. They are still evolving, still responding to internal heat and external forces. The Kuiper Belt is in a twilight era, still alive, but barely, still active, but fading. And then there is the question of the belt's overall shape. We mentioned the warp in the outer plane, but that's not the only strange geometric feature. The Kuiper Belt is not a flat ring like the main asteroid belt. It is a donut. Objects have a wide range of inclinations, from near zero to more than 30 degrees. The belt is thick, puffy, almost three-dimensional. This is in stark contrast to the inner asteroid belt, which is a thin disk. The difference is a direct result of Neptune's gravitational stirring. Neptune acts like a blender, shaking up the orbits and scattering objects into tilted paths. The result is a structure that looks more like a torus than a ring. But even within that donut, there are substructures. There is a sharp outer edge at about 50 astronomical units, where the density of objects drops off dramatically. This is called the cold classical cutoff. Beyond that, the density of the belt declines, but it doesn't disappear. There are objects at 60, 70, even 100 astronomical units. Some of them, like Sedna, have orbits that take them out to nearly 1,000 astronomical units. These extreme objects may belong to a separate population, the inner Oort cloud, or they may be part of a scattered disk that blends into the distant comet reservoir. And here is the terrifying implication. We have no idea where the Kuiper Belt ends. The boundary is not sharp. It fades into the unknown. And beyond that unknown, there may be a planet. Let's revisit the missing mass problem, but this time with a new perspective. We already know that the current mass of the Kuiper Belt is far less than what models predict. But here's a question. Are we even measuring the right thing? When we compute the mass of the belt, we are only counting objects larger than about 100 kilometers in diameter. Below that size, our telescopes cannot detect them directly. We can only infer their existence from the collisional cascade and from the dust we see in the infrared. So, when we say the belt has 1/16 of an Earth mass, that number is an upper limit based on what we can see. The actual mass could be higher, hidden in smaller objects, but the problem is worse than that. Even if we account for unseen small objects, the total mass still falls far short of the predicted 20 Earth masses. The discrepancy is not a measurement error, it is a fundamental mystery. Either the models of solar system formation are wrong, or most of the mass was ejected, or it's hiding in a form we haven't considered. What if the missing mass is not missing at all? What if it coalesced into a planet that we haven't found yet? A planet with a mass between that of Mars and Earth, orbiting at a distance of 60 to 100 astronomical units, could account for the gravitational warp we see in the outer belt. It would also explain the strange, highly elliptical orbits of Sedna and other extreme trans-Neptunian objects. That hypothetical planet is known as Planet 9. It is not a fringe hypothesis. It is a serious prediction based on gravitational anomalies. The evidence is circumstantial, but it is mounting. If Planet 9 exists, it would be a dark, frozen world, barely reflecting any sunlight, with an orbit that takes thousands of years to complete. It would be a giant among the Kuiper Belt objects, a hidden monarch ruling over a kingdom of ice. And if it exists, it would mean that the Kuiper Belt is not just a collection of debris. It is a system with a planet-sized body at its heart, a body that has sculpted the entire region. But what if Planet 9 does not exist? Then the warp and the missing mass would be even more terrifying. Because if no planet is causing the warp, then something else is. Perhaps a passing star, long gone, left its gravitational fingerprint on the belt. Or perhaps the warp is caused by the collective gravity of objects we cannot see, a dark matter effect on a small scale. Or perhaps our understanding of gravity itself is incomplete. Any of these alternatives would be revolutionary. So, the Kuiper Belt, this distant ring of ice, is not a boring, empty place. It is a laboratory for the most extreme dynamics in the solar system. It is a place where the ordinary rules of orbital mechanics break down, where binaries are either touching or drifting apart, where the plane of the belt twists and breathes, where most of the mass has vanished without a trace. It is a warning that our models of the solar system are incomplete, that there are things lurking in the darkness that we have not yet imagined. Consider the irony. The Kuiper Belt is named after Gerard Kuiper, the astronomer who predicted its existence in 1951. But Kuiper himself did not believe the belt could still exist. He thought that Pluto was as large as Earth, and that its gravity would have cleared the region, ejecting all the small objects into the Oort cloud. He wrote a paper concluding that the belt had already dispersed. Only in 1978, with the discovery of Charon, did we learn that Pluto was tiny, only 0.2% of Earth's mass. The belt exists precisely because Pluto is small. Kuiper made the right calculation using the wrong numbers. And so, today, we talk about the Kuiper Belt, named after a man who argued that it did not exist. That is the final terrifying irony of this region. It is a place that defies expectations. It is a place that hides its secrets. It is a place that is slowly, inevitably, grinding itself to dust, and we are only beginning to understand it. In the coming years, new telescopes, like the Vera C. Rubin Observatory in Chile, will scan the sky for moving objects, searching for the hidden planet and mapping the outer reaches of the belt. The New Horizons spacecraft, which gave us our first close-up look at Arrokoth in 2019, is still healthy and may visit another KBO in the 2030s or 2040s. We are on the cusp of a new era of exploration, but as we push deeper into the Kuiper Belt, we must be prepared for more surprises. Because if the history of this region has taught us anything, it is that what we think we know is almost certainly wrong. The belt is not what it seems. It is more dynamic, more bizarre, and more terrifying than any textbook could ever convey. The Kuiper Belt is not a quiet graveyard. It is a restless, dying structure, bent by unseen forces, emptied of its ancient riches, and haunted by the ghost of a planet we have not yet found. And as the sun ages and the solar system marches toward its eventual decay, the belt will continue to fade, to erode, to vanish into the void. But for now, it is still there, waiting, watching, warping, and daring us to understand it. And perhaps that is the most unsettling truth of all. The Kuiper Belt is not just a distant curiosity. It is a mirror held up to our own ignorance. We look out at the edge of the solar system and see a structure that should not exist, a mass that has vanished, a warp that defies explanation. Every time we think we have it figured out, the belt throws another contradiction at us. Let's step back for a moment and address a fundamental question that might be gnawing at you. How do we even know the Kuiper Belt is real? After all, for decades after Gerard Kuiper's prediction, no one had seen a single object out there besides Pluto. The belt was theoretical, a mathematical ghost. Then, in 1992, David Jewett and Jane Liu spotted a tiny speck of light moving against the background stars. That speck was 1992 QB1, later named Albion. It was the first confirmed Kuiper Belt object beyond Pluto and Charon. Since then, we have cataloged thousands. But the skeptics among you might still ask, are we sure these objects are really a belt? Could they be random stragglers? The evidence is overwhelming, and it comes from multiple independent sources. First, the sheer number of objects. Statistical surveys show that there are likely hundreds of thousands of Kuiper Belt objects larger than 100 kilometers in diameter, and billions of smaller ones. The distribution is not random. It follows a pattern. There is a dense core between 42 and 48 astronomical units, and a steep drop-off beyond 50 AU. That is the signature of a structured belt, not a random scattering. Second, the orbits. The objects in the classical Kuiper Belt have low eccentricities and modest inclinations, indicating they formed in place and have been relatively undisturbed. If they were random captures from elsewhere, their orbits would be chaotic. Instead, they are orderly. They share a common plane, albeit a warped one, and their orbital periods are resonant with Neptune's in many cases. That is not coincidence. It is gravitational sculpting. Third, the dust. The Kuiper Belt produces a faint infrared glow, a thermal emission from the dust generated by collisions. This glow has been detected by space telescopes like Spitzer and Herschel. The dust is too warm to come from the distant Oort cloud and too cold to come from the inner solar system. It is exactly what you would expect from a grinding, collisional belt of icy bodies. Fourth, the comets. We know that short-period comets, those that return every few decades, come from a flattened disk beyond Neptune, not a spherical cloud. The Kuiper Belt is the only source that fits. When we study comets like 67P Churyumov-Gerasimenko, visited by the Rosetta mission, we see surfaces and compositions that match Kuiper Belt objects. The belt is not a theory. It is a cause and effect. Fifth, the direct imaging. Telescopes like Hubble and Keck have imaged Kuiper Belt objects directly, resolving their surfaces in some cases. We have seen the binary systems, the rings, the contact binaries. We have watched them move across the sky. There is no doubt. The Kuiper Belt is as real as the asteroid belt. It is just farther away, colder, and far more mysterious. Now, let's dig deeper into the missing mass paradox, because that is the true heart of the terror. Think of it this way. You have a bank account. According to all your records, you should have $20,000. But when you check the balance, you find only $1.20. And the bank insists that is correct. No errors, no hidden fees. Where did the other $19,998.80 go? That is the situation astronomers face with the Kuiper Belt. The predicted mass of the primordial planetesimal disk beyond Neptune is between 20 and 50 Earth masses. That number comes from models of solar system formation, which are based on the amount of material needed to build the gas giants and the timing of their migration. These models have been successful in explaining many other features of the outer solar system. The missing mass is not a minor discrepancy. It is a chasm. One possible explanation is that Neptune itself was the thief. During its outward migration, Neptune scattered most of the planetesimals inward toward the Sun, or outward into interstellar space. The belt we see today is just the leftover tailings of that process, a few grains left in a pan after the gold has been panned out. But here is the problem. The simulations that show Neptune scattering most of the mass also predict that the belt should be much more depleted than it actually is. The observed belt is still too massive relative to the scattered debris. The numbers do not add up. Another idea is that the missing mass was ground down into dust and then blown away by solar radiation pressure and the solar wind. This is the collisional cascade. Over billions of years, objects collide, shatter, and produce smaller fragments. Those fragments collide again, creating even smaller pieces. Eventually, the particles become small enough that the sun's light pushes them away. This process is ongoing today. The Kuiper Belt is slowly grinding itself to dust, and that dust is escaping into the void. But even if we assume a high collision rate from the beginning, it is difficult to explain the loss of 20 Earth masses. The cascade would need to be incredibly efficient, and it would have needed to start early, before Neptune had time to stir things up. Then there is the most unsettling possibility. The missing mass never existed. Perhaps our models of the early solar system are wrong. Maybe the protoplanetary disk was not as massive in the outer reaches as we think. Perhaps the gas giants formed more quickly and cut off the supply of material. Or perhaps the Kuiper Belt was never meant to be a belt at all. Maybe it is the remnant of a larger structure that was mostly ejected, and what we see is just the shadow of a much grander entity. But here is where it gets truly terrifying. The missing mass could be hiding in plain sight, in objects too small to detect but collectively enormous. Imagine 1 trillion comets, each the size of a mountain, spread across the outer solar system. They would barely reflect any light, and they would be too faint for our telescopes to see. But their combined mass could be immense. This is not a fringe idea. Studies of the dust emission and the number of small craters on Kuiper Belt objects suggest that there is a vast population of sub-kilometer bodies out there. Some estimates put the total mass of these small objects at several Earth masses. If that is true, then the missing mass is not missing at all. It was there all along, just hidden from our sight. But wait, if the small objects are so numerous, why haven't we seen their effects on the orbits of larger bodies? That is the catch. The gravitational influence of a diffuse cloud of small objects is different from that of a few large ones. If the missing mass is distributed among millions of tiny bodies, their combined gravity would be spread out and hard to detect. It would not cause the same kind of warp or resonance that a planet would. So, we cannot rule it out. And yet, there is another clue. The binary systems we discussed earlier, the ultra-wide pairs like 2001 QW322, are fragile. They should have been disrupted by passing stars or by Neptune's gravity long ago. The fact that they still exist means that the region where they reside is very sparsely populated. If there were a large number of small objects in that region, these binaries would have been destabilized. So, the small object explanation has its own problems. The belt is a puzzle that resists easy answers. Now, let's talk about the collisional cascade in more detail, because it is not just a mechanism for losing mass, it is a process that is actively reshaping the belt every day. When two Kuiper Belt objects collide, they do not always merge. Often, they shatter, producing a cloud of debris. Some of that debris falls back onto the larger bodies, creating impact craters. Some of it escapes as dust. Over time, the belt becomes a self-grinding mill. Every collision reduces the total mass because some fragments are ejected from the system. This is not a fast process. It takes billions of years, but it is relentless. What is terrifying is that this process is accelerating. As the belt gets thinner, the remaining objects have fewer neighbors, so collisions become rarer. But each collision that does occur is more likely to be catastrophic because the objects are more spread out and their relative velocities are higher. The belt is caught in a feedback loop. It is dying, but it is dying slowly and painfully. And when the sun eventually becomes a red giant, in about 5 billion years, the outer planets will move outward, and the Kuiper Belt will come under renewed gravitational assault. The sun's luminosity will increase, causing the ice in Kuiper Belt objects to sublimate, producing cometary activity. Many of those objects will become active comets, their orbits perturbed by a dying star. Some will fall into the sun. Others will be ejected. The belt will be stripped bare. In the end, after the sun has shed its outer layers and become a white dwarf, the Kuiper Belt may be reduced to a few scattered boulders, a ghostly relic of a world that once was. But that is billions of years away. For now, the belt is still here, still active, still hiding secrets. One of the most exciting frontiers in Kuiper Belt research is the search for more dwarf planets. We know of 5: Pluto, Eris. The answer is forever. In the vast, silent cathedral of space, a small, silent traveler is writing a story that will outlast us all. This is Voyager 1, and the question of how far it can travel has a simple, staggering answer. It will never truly stop. It will drift among the stars for eons, a permanent fixture in the cosmos long after the Earth from which it came has been erased. To understand this, we must not just measure in miles or kilometers, but in millennia. We must chart a course not just through space, but through deep, unfathomable time. Today, Voyager 1 is over 15 billion miles from Earth. A signal from it, traveling at the speed of light, takes more than 22 hours to reach us. It is the most distant human-made object in existence, a title it will almost certainly hold forever. It moves at a relentless 38,000 miles per hour. But this is just the opening sentence of an epic that spans cosmic eras. The immediate future is one of quiet, graceful decline. Voyager is dying, not from violence, but from cold, patient starvation. Its heart is 3 spheres of plutonium-238. As this radioactive material decays, it produces heat, which is converted into the precious few watts of electricity that power the spacecraft's brain and voice. But physics is inexorable. The plutonium has a half-life of 87.7 years. Every year, NASA loses about 4 watts of power. The engineers have performed a decades-long triage, switching off heaters, shutting down instruments one by one, conserving every joule of energy for the core systems that keep the antenna pointed at Earth. The mathematics are unforgiving. Sometime around 2025, the power will dip below the threshold needed to operate any of its remaining science instruments. The mission of discovery will end. Then, between 2030 and 2036, the last critical watt will fade. The temperature inside will plummet to near absolute zero. The transmitter will fall silent. On Earth, the giant radio ears of the Deep Space Network will listen intently one day and hear only the faint hiss of the universe. That will be the last whisper. After that, Voyager 1 transitions from a spacecraft to a relic, a ghost ship carrying a message, sailing into eternity. And here is the first great misconception to correct. Many believe that when Voyager's power dies, its journey is over. Nothing could be further from the truth. That moment is merely the end of its conversation with us. Its physical voyage is less than 1% complete. Others believe it has already left the solar system. This, too, is a matter of perspective. In 2012, Voyager 1 crossed a monumental threshold, the heliopause. This is the boundary where the outward pressure of the solar wind, a stream of charged particles blowing from the sun, meets the inward pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. Crossing this boundary made it an interstellar traveler. But it did not leave the solar system. The true domain of our sun is defined by gravity, not wind. And gravitationally, our system is enclosed by a vast, spherical shell of icy debris called the Oort cloud. This is the source of our long-period comets, a frozen repository of primordial material from the solar system's birth. The inner edge of this cloud is believed to begin roughly 2,000 times farther from the Sun than Earth is. Its outer edge may extend 100,000 times that distance, or even farther. Traveling at its incredible speed, when will Voyager 1 reach this frontier? Not for another 300 years. It will spend 3 centuries drifting through the quiet, near-perfect vacuum before it even enters the Oort cloud. And to completely pass through it, that will take approximately 30,000 years. Let that time scale sink in. When Voyager 1 finally exits the gravitational grasp of our Sun and becomes truly adrift in the galactic tide, human civilization will be 300 centuries older. All of recorded history fits into a fraction of that time. Our languages, our nations, our very species may be unrecognizable. Yet, the trajectory calculated by engineers in 1977 will still be playing out with immutable precision. What is the environment like on this journey? For the craft itself, it is a state of near-perfect preservation. Space is an exquisite museum. There is no oxygen to cause rust, no moisture to enable corrosion, no weather to cause erosion. The primary threat is a random impact from a micrometeorite, but space is so empty and Voyager's cross-section so small that the probability of a catastrophic strike over the next million years is vanishingly low. It will fly on, intact, a fossil in a vacuum-sealed display case. Its first notable encounter after leaving the Oort cloud will occur in about 40,000 years. It will pass within 1.6 light-years of a small, dim red dwarf star known as Gliese 445 in the constellation Camelopardalis. This is not a close approach by cosmic standards. It's still over 100,000 times the distance from Earth to the Sun. It will be completely unaffected by the star's gravity, sailing past like a ship glimpsing a distant lighthouse. By this point, 40 millennia have passed. The probe is an ancient artifact from a civilization that may itself be ancient history. The milestones continue on a scale that bends the mind. In roughly 296,000 years, Voyager 1 will pass within about 4.3 light-years of Sirius, the brightest star in our night sky. Again, It is a distant, silent passage. On Earth, in that time, continents will have shifted. Ice ages will have come and gone dozens of times. Mountain ranges will have risen and been worn flat. The entire tapestry of life may have been rewoven. And yet this machine, built with 1970s technology, follows its preordained path. Now, accelerate the clock further, into the millions of years. At the 1 million year mark, Voyager will be about 88 trillion miles from its launch point. It is now a true galactic wanderer, drifting through the Orion arm of the Milky Way. It may pass within a few light years of various anonymous red dwarf stars. Structurally, it is likely still intact. The aluminum of its structure, the gold plating on its famous record, the silicon of its chips, all are stable in the void. The golden record, a time capsule of sounds and images from Earth, is still technically playable, though there is nothing for light years in any direction that could play it. By 10 million years, the distance stretches toward a quadrillion miles. Here, we must introduce a new complexity. Nothing in the galaxy is static. Our Sun, along with every star Voyager passes, is orbiting the center of the Milky Way. The Sun completes one galactic orbit every 250 million years. So Voyager's path, while straight from its own perspective, becomes a complex, weaving spiral when viewed from the galaxy's core. It is like a single car driving in a straight line on a vast, spinning roundabout where all the other cars are also moving. Its trajectory relative to the Sun and other stars is constantly, slowly curling. Jump now to timescales where stars themselves are born and die. 1 billion years from now, Voyager has traveled quadrillions of miles. In this time frame, the galaxy has changed. Many of the bright stars we see today have exhausted their fuel, ending as white dwarfs, neutron stars, or in supernova explosions. New stars have ignited from stellar nurseries. Entire stellar generations have turned over. Voyager itself is now older than most of the stars it glides past. And what of its creator, the Sun? In about 5 billion years, our Sun will begin its death throes. It will swell into a red giant, likely engulfing Mercury, Venus, and possibly Earth. It will then shed its outer layers and collapse into a fading Earth-sized ember called a white dwarf. This cataclysm will be the final end for any earthly remains. But Voyager 1 will be oblivious. By that time, it will be tens of quadrillions of miles away. It will receive no increased light, feel no gravitational shift. It will not witness the death of its star. The Earth it knew will have been gone for billions of years. But the probe, carrying a record of that world, continues its endless migration. The cosmos itself has a life cycle. Current models suggest that in trillions of years, the universe will enter a degenerate era. Star formation will have ceased. The remaining lights will be the cooling corpses of stars, white dwarfs and neutron stars. Galaxies will have evaporated as their stars drift apart in an ever-accelerating, expanding universe. The cosmos will grow dark and cold. Even in this dying universe, Voyager could, in theory, persist. Over timescales so vast, they are written with exponents, 10, 30 years and beyond. Even the atomic nuclei in its structure may decay via quantum tunneling, or, by sheer statistical chance over these incomprehensible eons, its path could be bent by a chance gravitational encounter, sending it into a dead star or a black hole. but these are speculations on timescales that make the current age of the universe seem like a blink. So, to return to the original question with the full weight of this timeline, how far can Voyager 1 travel? The answer is not a number. It is a duration, forever. It will never coast to a stop. There is no friction in the vacuum of interstellar space to slow it down. No force, save the impossibly weak and distant tug of stars it never approaches closely, acts upon it. Its velocity is a permanent testament to the explosive energy of its 1977 launch and the gravitational slingshots of Jupiter and Saturn. The distances become meaningless. They simply accumulate infinitely. In 40,000 years, it passes a star. In 300,000, another. In millions of years, it wanders the galactic suburbs. In billions, it outlives its sun. In trillions, it drifts through a darkening cosmos. This transforms Voyager from a probe into something else entirely. It is a monument, a tombstone for humanity, not carved in stone but in trajectory and velocity. It is our most enduring artifact. On Earth, wind, water, and tectonic shifts will erase all our cities and monuments within a few 100,000 years. The Earth itself will be consumed, but Voyager, in its silent, deep freeze exile, will endure. The golden record it carries is not just a message for some hypothetical alien finder. It is a message to the future itself, cast into the cosmic ocean with no expectation of retrieval. It is proof that we were here, that we wondered, that we reached out. The final frontier for Voyager is not a place in space. It is a point in time beyond our ability to comprehend, where our species, our planet, and even our star are just faint memories in the history of the galaxy. Its journey is a lesson in humility and ambition. We built something so fragile yet so resilient that its echo will travel the galaxy long after our own voices have faded into silence. It is, in the most literal sense, our eternal voyage. But to truly comprehend the scale of this forever, we must zoom in from the cosmic to the microscopic, to the very engineering that allows this forever to be possible. Voyager's immortality is not an accident. It is the direct result of deliberate, foresighted choices made by engineers working with slide rules and paper schematics in the 1970s. Every contingency they planned for, every redundancy they built, was a bet placed on a future they would never see. And now, that bet is paying dividends in deep time. Consider the power system. The 3 radioisotope thermoelectric generators, RTGs, are marvels of passive engineering. They have no moving parts. The natural decay of plutonium-238 produces heat, and thermocouples convert that heat directly into electricity. It is a slow, inexorable process tied to the half-life of the material. This is why the decline is so predictable, allowing for a decades-long managed retreat of systems. Engineers didn't just build a power source, they built a countdown clock with a known rhythm, enabling them to meticulously plan the end of the mission's active life. The spacecraft's vitality is literally tied to nuclear physics, a clock that ticks for centuries. Or consider the fault protection. The spacecraft's computer systems are antiques, with less memory than a modern digital wristwatch. Yet they are robust, radiation-hardened, and possess a layered self-awareness. The now famous incident in 2022, where the Attitude and Articulation Control Subsystem, AACS, began sending garbled telemetry, is a perfect case study. For months, The spacecraft was effectively speaking in gibberish about its own orientation, yet it never entered safe mode. Why? Because its other systems confirmed it was still pointing its antenna correctly. The signal strength on Earth was unwavering. The spacecraft itself had enough innate intelligence to recognize that while one sensor's report was nonsense, the overall mission, pointing the antenna, was still being accomplished. It prioritized function over form, continuing to send pristine scientific data from its other instruments even as it babbled incoherently about itself. The fix, when it came, was a simple remote command to switch to a backup data routing system. A problem 15 billion miles away was diagnosed and solved by humans who could only send commands at the speed of light and wait 45 hours for a reply. This is not just engineering. It is a form of deep space medicine, practiced across a gulf so vast it defies human intuition. This resilience extends to the very structure. Voyager was built to survive the asteroid belt, a region once feared to be a chaotic shooting gallery. It was built to handle the intense radiation belts of Jupiter. Its components were tested to extremes that seemed absurd at the time. Now, those same qualities defended against the quiet, cold hostility of interstellar space. The primary enemy is not impact, but entropy, the gentle, universe-wide decay of ordered energy into disordered heat. Voyager fights this not with action, but with sheer, stubborn material integrity. Its aluminum structure, its beryllium copper antenna, its gold-plated records. These materials don't oxidize, don't decay in the vacuum. They are subject only to the sublimely slow processes of cosmic ray sputtering, where individual atoms might be knocked off over millions of years, and the even slower creep of metallic fatigue at temperatures near absolute zero. In human terms, it is immortal. It will remain recognizable as a crafted object for timescales that dwarf human history. This brings us to a profound and unsettling thought. Voyager 1's journey is a mirror that reflects the transient nature of its creators. We are building a legacy that will outlast us by orders of magnitude. The pyramids are a few thousand years old. The oldest human artifacts are stone tools a few million years old. Voyager and its twin Voyager 2 will be intact, identifiable artifacts tens of millions, even hundreds of millions of years into the future. They will be drifting through space long after every trace of the civilization that built them has been scoured from the surface of Earth by wind, ice, and geologic upheaval. In a very real sense, these two probes will become the final and longest-lasting monuments to the human species. The Golden Record is not merely a greeting card. It is our civilization's last will and testament, filed with the cosmos. What, then, does it mean to travel through the Oort cloud, this unimaginably vast and lonely realm that will be Voyager's home for 30,000 years? This is not a dense field of ice blocks. It is a sphere of profound emptiness, sparsely populated by frozen primordial bodies in slow, vast orbits. Voyager will traverse this region like a single dust mote drifting through an empty cathedral. The chances of it coming close enough to any Oort cloud object to be seen, let alone impacted, are infinitesimally small. Its passage will be utterly dark and silent. The sun will have shrunk to a point of light barely brighter than other stars, a faint reminder of a gravitational tether that still weakly holds. For 30 millennia, the probe will be a prisoner of the sun's gravity, albeit in its most distant, feeble dungeon. Its escape will be so slow as to be imperceptible. Once free, it enters the true interstellar medium. The data it has sent back in recent years has already revolutionized our understanding of this region. It is not a uniform, placid sea. Voyager discovered that the boundary of our solar bubble, the heliopause, is foamy with magnetic bubbles, a turbulent zone where the sun's magnetic field lines break and reconnect. The interstellar medium itself is a patchwork of clouds. Voyager is currently in what is called the local interstellar cloud, a region of slightly denser hydrogen and helium. In about 2,000 years, it will likely enter the next cloud, the G cloud, home to the Alpha Centauri system. These clouds are like different currents in a galactic ocean, each with its own density and temperature. Voyager will sample them all, silently, its instruments long dead, becoming a physical probe moving through environments we can currently only study from afar. Its trajectory is not a straight line out of the galaxy. The Milky Way is a rotating disk, and Voyager is caught in its dynamics. While it speeds away from the Sun at 17 kilometers per second, the Sun itself is orbiting the galactic center at about 220 kilometers per second. From a galactic perspective, Voyager's path is a complex, slowly evolving spiral. It orbits the galactic center just as the Sun does, but on a slightly different path with a slightly different tilt. It will oscillate above and below the galactic plane, completing a galactic orbit roughly every 225 million years, but never in perfect sync with its stellar siblings. It is a lone wanderer on a galactic pilgrimage, its route a testament to the initial velocity imparted by a Titan III rocket and the gravity of Jupiter. The stellar encounters we can predict, Gliese 445 Sirius, are mere flashes in this billion-year journey. They are not destinations, but temporal landmarks in a voyage without a map. In the immense spans between these landmarks, the galaxy will transform. Stars Voyager once knew will die. New constellations will form from stellar nurseries it will never see. And through it all, the silent dark probe persists, a piece of 20th century technology fossilized in the 21st, destined to become an anachronism of unfathomable age. Could it ever be found? The golden record was crafted with that hope, however faint. The probability is so low as to be effectively zero, but not quite zero. In a galaxy of hundreds of billions of stars, over quintillions of years, even the most unlikely events may occur once. If some unimaginably advanced spacefaring civilization were to ever stumble upon it, perhaps swept up by a vast interstellar harvesting operation or detected by a sensitive survey of anomalous non-natural objects, what would they make of it? They would be archaeologists of the cosmos, uncovering a relic from a long-vanished species on a world that no longer exists. The golden cover with its engraved instructions, the record itself with its sounds of Earth, the images of human beings, all of it would be a puzzle box from the deep past. It would tell them not just about us, but about our yearning to be known, our desire to shout our existence into the void. In that potential far-fetched moment of discovery, Voyager's ultimate purpose would be fulfilled, to testify that we were here, that we wondered, and that we tried to reach out. But the more likely, and in some ways more poetic, fate is that it will never be found. It will simply travel on, a permanent addition to the galaxy's background population of inert matter. It will become a piece of galactic driftwood, a tiny, artificial planetesimal orbiting the heart of the Milky Way until the end of stars. This, perhaps, is the most honest answer to how far can it travel. It will travel until the universe itself changes shape in ways we can barely model. Current cosmology suggests a future of expanding emptiness, the heat death, where all energy is evenly distributed and no work can be done. In such a universe, Voyager would still exist as a configuration of atoms, drifting in perfect darkness and perfect cold. Its journey would have no witness, not even itself. It would simply be, a monument without an audience, a story without a reader. Its travel would be absolute, pure, and eternal motion in a static, infinite canvas. So, when we ask, how far can the Voyager 1 travel? We are asking a question about infinity. We are asking about the legacy of a curious species inscribed on a metal disk and flung into the dark. We are asking about the endurance of memory in a universe that seems built on forgetting. The probe's distance from Earth is a number that updates daily, growing larger. But its true distance is measured in the future it has yet to traverse, a future that stretches beyond the life of our sun, beyond the glow of our galaxy, into the cooling embers of the cosmos itself. Voyager 1 is humanity's first step into eternity. It is our message in a bottle, our time capsule, our tombstone, and our ambassador. Its journey is finite only in the sense that the matter composing it will one day, after eons upon eons, succumb to proton decay or a random quantum event. But in any time scale that holds meaning for life, for consciousness, for civilization, it is endless. It will travel as far as time allows, carrying a whisper of the pale blue dot into the everlasting night. This galactic orbit it shares with our sun, yet undertakes alone, introduces another fascinating dimension to its travel: precession. Just as a spinning top wobbles on its axis, Voyager's orbital path around the galactic center will slowly rotate. Over hundreds of millions of years, its elongated track will twist, tracing a complex rosette pattern in the vast disk of the Milky Way. It will never retrace its own steps. Its journey is a unique, non-repeating path through the galaxy's star fields, a single, infinite line drawn in the ledger of cosmic motion. And what of the environment through which it will drift for these eons? The interstellar medium is not perfectly empty. It contains fine dust grains, perhaps no larger than a virus. Over tens of millions of years, these microscopic particles will have a sand-blasting effect, a process called sputtering. Atom by atom, the surface of Voyager's aluminum skin and its golden record cover will be eroded. The erosion rate is minuscule, perhaps a millimeter every few 100 million years. But given enough time, even this gentle, persistent rain will wear down its features. The engraved instructions on the record cover may become faint, then illegible. The spacecraft's shape will soften, its sharp edges rounded by cosmic sandpaper. Yet its core mass, its essential structure, will remain intact for far longer. It is a lesson in geological timescales applied to a human artifact. It will weather the galaxy, not in centuries, but in galactic years. This leads to a staggering consideration: the possibility of stellar close encounters that are not gentle passes. The galaxy, for all its emptiness, is dynamic. Stars are born in clusters and can be ejected, becoming hypervelocity stars racing through the Milky Way. While rare, a close gravitational interaction with a passing star, or more likely, a rogue brown dwarf or stellar mass black hole, could significantly alter Voyager's course. it could be flung onto a faster trajectory out of the galaxy entirely, becoming a true intergalactic traveler. Conversely, a close gravitational encounter could send it plunging on a more radial orbit toward the crowded galactic bulge. The probabilities of such dramatic events are vanishingly small over a few billion years. But as the timeline stretches toward 1 trillion, they become non-zero. Voyager's path, so precisely calculated for its first century, becomes subject to the whims of celestial chaos over the deep future. Its trajectory is only certain in the short term. In the long term, it is a statistic, a subject of gravitational probability. Within this incomprehensible time span, even the Golden Record's medium faces a silent adversary. The copper disk, plated with gold and encased in its protective aluminum jacket, is susceptible to the internal effects of radiation. The constant bombardment by cosmic rays over millions of years can induce gradual changes in the crystalline structure of the materials, potentially degrading the analog information stored in the record's grooves. The images and sounds we so carefully inscribed are, in the longest view, temporary. They may last hundreds of millions, even billions of years, a duration that dwarfs all of human history, but they are not infinitely durable. The message may fade before it is ever found, leaving only a strange, sculpted artifact of unknown purpose. This imbues the record with a poignant duality. It is both an attempt at eternal communication and a testament to the inevitable entropy that claims all ordered things, even in the vacuum of space. Yet, long after the grooves have become unreadable, the artifact itself will speak volumes. Its geometry is undeniably artificial. The hexagonal bus, the conical RTG housing, the large parabolic dish, these are shapes not found in nature. Any future finder, even one with no concept of human technology, would recognize it as a constructed object. It would be a mystery, a fossil of intelligence. In this way, Voyager's very form is a more universal message than the specific contents of the record. It says, simply, a maker existed. As we contemplate these deep futures, we must also confront the limits of our own models. Our predictions of Voyager's path for the next few million years are robust, based on well-mapped stellar positions and velocities. But beyond that, the uncertainty grows. The Milky Way will merge with the Andromeda Galaxy, beginning in about 4 billion years. This process, taking hundreds of millions of years, will gravitationally stir the stellar population. While direct stellar collisions are unlikely, the tidal forces and changing gravitational potentials will scatter stars and Voyager with them onto new, unpredictable orbits. Our probe will be a witness to this cosmic event.
In 1977, humanity embarked on one of its most audacious ventures, launching the Voyager spacecraft into the vastness of space. These twin probes, symbols of our insatiable curiosity, ventured far beyond the familiar planets, aiming to uncover the mysteries of the very edges of our solar system. As we journey with the Voyagers, we bear witness to their incredible odyssey, exploring realms where no probe has ventured before. Their golden records, a testament to the human spirit, carry our greetings to any who might find them in the cosmic ocean. Yet our exploration does not end with the Voyagers. Far beyond the gas giants, in the shadowy fringes of our solar neighborhood, lies Pluto. This distant world, once a planet in our textbooks, now stands as a gateway to the outer solar system. Through the eyes of new horizons, we have glimpsed its wonders, towering ice mountains, vast nitrogen glaciers, and the enigmatic heart-shaped Tombaugh Regio. Pluto, in its silent beauty, challenges our understanding and invites us to delve deeper into the unknown. Beyond Pluto, whispers of an unseen world stir the scientific community. This elusive Planet 9, hidden in the darkness, bends the paths of distant objects with its gravitational embrace. Its existence, inferred from the strange orbits of trans-Neptunian objects, hints at a world yet to be seen, a planet at the very boundaries of our solar system. Join us on a journey to the mysteries on the boundaries of the solar system, where the Voyager saga, the enigmatic Pluto, and the elusive Planet 9 await. In the sweltering summer of 1977, a cosmic opportunity loomed on the horizon. The planets of our solar system were aligning in a way that happens only once every 176 years. This rare celestial event opened the way to the unknown and gave us a chance to embark on a grand journey to the outer planets. Using this happy coincidence, NASA engineers and scientists conceived of a mission in which two probes would slingshot from planet to planet, using the gravitational pull of each to propel them farther into the depths of space. The technological marvels that were Voyager 1 and Voyager 2 were equipped with the most advanced instruments of their time. From imaging systems capable of capturing Jupiter's swirling storms to magnetometers designed to study Saturn's magnetic fields, these spacecrafts were to rewrite our understanding of the solar system. But the journey to the launch pad was fraught with challenges, budgetary constraints, technological hurdles, and the boldness of the mission objectives pushed the team to the limit. Every component of the spacecraft had to be painstakingly tested, every system optimized for the rigors of space. As the launch dates approached, the excitement was palpable.
3, 2, 1. MDS, we have ignition, we have a liftoff.
Soaring into the skies, these twin messengers carried with them the hopes and dreams of all mankind, embarking on a journey that would forever change the way we think about the cosmos. When Voyager 1 and Voyager 2 traveled beyond the asteroid belt, they were greeted by the colossal presence of Jupiter, the gas giant that gravitationally dominates our solar system. These encounters set in motion a series of groundbreaking discoveries that would overturn our view of the outer planets. Armed with a host of sophisticated instruments, the probes peered into the planet's turbulent atmosphere, revealing the dynamic and violent nature of its storms. The imaging science system, a key component of Voyager's arsenal, captured stunning details of the big red spot, a storm larger than Earth itself, and revealed never-before-seen features. But perhaps one of the most unexpected discoveries was the existence of Jupiter's thin ring system, a ghostly band of dust and particles girdling the planet. This discovery, made possible by the ship's photopolarimeter, disproved the notion the rings were a feature exclusive to Saturn. Among Jupiter's moons, Io stood out for its fiery temperament. The observations revealed a world with volcanic activity, the first time such phenomena have been observed outside of Earth. Moreover, Io is the most volcanically active body in our system, its surface forever changing under the inexorable forces of its interior. Images of towering plumes and lava flows have changed our understanding of geologic processes in the solar system. As the Voyagers continued their journey to Saturn, unprecedented beauty awaited them. The complex and intricate structure of Saturn's rings came into view, and the probe's cameras captured the subtle interplay of light and shadow among the countless ice particles. The scientific instruments aboard the spacecraft, especially the radio system, played a crucial role in studying the composition and dynamics of Saturn's rings. The data collected revealed the complex structure of the rings, including the mysterious gaps and braids phenomena whose formation continues to intrigue scientists to this day. Titan, Saturn's largest moon, was another highlight of the mission. Shrouded in a thick atmosphere, Titan was a world of mystery, its surface hidden from view. However, thanks to the ingenuity of Voyager's instruments, glimpses of this mysterious moon suggested the presence of liquid hydrocarbon lakes and a complex weather system, sparking curiosity and speculation about the possibility of life on it. The Voyager 1 and Voyager 2 encounters with Jupiter and Saturn have not only expanded our knowledge of the hot gas giants, but have also opened new frontiers in the exploration of the outer solar system. In the cold and distant reaches of our solar system, Voyager 2 set out for a solitary encounter with Uranus, the enigmatic ice giant. This historic encounter in January 1986 offered a glimpse of a world that had previously been just a pale blue dot in Earth-based telescopes. Uranus has presented an enigma to scientists with its peculiar tilted axis lying almost parallel to the plane of the solar system. This unusual orientation, with poles that alternately bask in the sun and languish in decades of darkness, has a profound effect on the planet's weather and atmospheric dynamics. As Voyager 2 approached, its instruments, including the narrow-angle imaging science system camera, began to capture unprecedented images of Uranus's atmosphere and its suite of moons and rings. The pale blue color of Uranus hid the complex structure of the atmosphere. Faint bands of clouds and previously invisible rings girdling the planet. One of the most striking discoveries was the nature of Uranus's magnetic field, revealed by the spacecraft's magnetometers. Unlike the Earth, whose magnetic axis coincides exactly with the axis of rotation, Uranus's magnetic field was found to be significantly displaced and tilted, suggesting a complex and possibly multi-layered internal structure. Leaving Uranus behind, Voyager 2 continued its journey to Neptune, the most distant of the known planets. In August 1989, mankind saw Neptune for the first time up close. A dynamic and turbulent world, at the center of which was the Great Dark Spot, a storm the size of the Earth. Neptune's atmosphere, buffeted by supersonic winds, paints a portrait of a planet alive with weather disasters. The spacecraft and its suite of instruments have delved into the mysteries of these winds, capturing the movement of cloud formations and the complex pattern of Neptune's faint rings. Among Neptune's moons, Triton stands out for its retrograde orbit and geologically young surface. Voyager 2 images of Triton showed a frozen landscape dotted with geysers spewing nitrogen gas and dust into space, hinting at a geologically active interior. Voyager 2's encounter with Uranus and Neptune have expanded the frontiers of our knowledge, revealing the diversity and dynamism of the outer planets. These fleeting visits have provided a treasure trove of data that continues to influence our understanding of the icy giants of the solar system. Moving farther and farther away, with limited resources, mission controllers face the difficult question of which instruments should be left operational. To extend the life of the mission, non-essential systems, including the camera, were planned to be shut down permanently. But in a moment that epitomized the human spirit of exploration and reflection, astronomer Carl Sagan proposed a bold idea. Before the camera goes silent forever, he suggested that Voyager 1 take one last picture of Earth, a farewell shot of our home planet from the edge of the solar system. On February 13, 1990, the spacecraft warmed up its cameras for 3 hours. The spacecraft's science platform then took a series of images from a distance of about 4 billion miles that would later be combined into a mosaic of the solar system. Among the myriad scientific achievements, it was Voyager 1's gaze toward its home planet that captured the collective imagination of humankind. That pale blue dot, is a testament to our insignificance in the vast expanse of space and a poignant reminder of our shared responsibility to preserve and protect the only home we have ever known. In an odyssey that stretches beyond the bounds of human perception, Voyager 1 and Voyager 2 traveled beyond the confines of our solar system, traversing the vast, uncharted territories of interstellar space. This monumental passage marked the first time humanity had traveled beyond the heliopause, the boundary where the sun's influence wanes and the mysteries of the cosmos are fully revealed. The heliopause is the extreme boundary of the solar zone, or domain, where the solar wind, a stream of charged particles emanating from the sun, meets the interstellar medium, the matter that fills the space between the stars in our galaxy. At this boundary, the external pressure of the solar wind is balanced by the internal pressure of interstellar gas and magnetic fields, creating a turbulent region that marks the end of the sun's influence. When Voyager 1 approached this boundary in August 2012, it became the first man-made object to cross interstellar space, providing scientists with direct measurement of the boundary for the first time. At that point, the instruments aboard the spacecraft, though developed in the 1970s, continued to transmit invaluable data back to Earth, recording a sudden decrease in solar wind particles and a corresponding increase in high-energy cosmic rays from outside our solar system, increasingly revealing the history of our universe. Voyager's journey beyond our solar system has not only expanded our understanding of the universe, but it's also paved the way for future endeavors in the never-ending quest to explore space. Their legacy is captured in the vast amount of data about the outer planets, their moons, and the heliosphere, and continues to be a cornerstone for scientific research, influencing the study of fields ranging from planetology to astrophysics. These missions have provided insights into the dynamics of planetary atmospheres, the structure of rings, and the nature of magnetic fields, setting the stage for subsequent missions. In the spirit of Voyager's pioneering voyage, subsequent missions have been designed to delve deeper into the mysteries uncovered by the twin spacecraft. For example, the Cassini-Huygens mission expanded our knowledge of Saturn by deeply analyzing the planet's rings, moons, and atmosphere. Similarly, the Juno mission looked beneath Jupiter's clouds, revealing the secrets of its internal structure and magnetic field. Looking to the future, the scientific community is clamoring for dedicated missions to Uranus and Neptune. These proposed missions are aimed at a comprehensive study of the icy giants, exploring their unique atmospheres, complex ring systems, and diverse moons. Such studies will not only improve our understanding of these enigmatic planets, but will also shed light on the formation and evolution of the solar system. Among the myriad scientific instruments and revolutionary technologies aboard the Voyager spacecraft is a message not for us, but for the unknown, for the future, or perhaps for other space dwellers. That message is the Golden Record, a 12-inch gold-plated copper disc on which are recorded sounds, images, music, and greetings from Earth. The Gold Record serves as a time capsule, a snapshot of humanity and our planet at the end of the 20th century. Its contents have been carefully selected to show the diversity of life and culture on Earth, from the sounds of nature, such as bird song and the sound of the ocean, to music from different cultures and eras, including Bach, Beethoven, and traditional music from around the world. Decisions about the content of the Golden Record were guided by the desire to present a comprehensive picture of Earth and humanity. The team, led by Carl Sagan, put a lot of thought into including content that would not only convey the complexity and beauty of life on Earth, but also reveal fundamental scientific concepts, such as the structure of DNA and the location of our planet in the solar system. The cover of the Golden Record is decorated with symbolic instructions, the universal language of science and mathematics, designed to tell potential aliens how to decipher the disk. These symbols explain the origins of the record and provide instructions on how to play the audio content, ensuring that the message is understood throughout the space, transcending language and cultural barriers. The record is a testament to humanity's hope and desire for contact, communication, and connection, not only with our future generations, but perhaps with other beings who will one day find this bottle tossed into the cosmic ocean, carrying a message of a small, distant world full of life and dreams. As Voyager 1 and Voyager 2 continue their silent odyssey into the depths of interstellar space, the task of keeping in touch with these distant explorers is becoming increasingly difficult. Billions of miles from Earth, the faint signals transmitted by the spacecraft take more than 22 hours to cross the cosmic expanse and come like whispers from the void. The Deep Space Network, an array of giant radio antennas scattered around the globe, serves as the ears of the Earth, listening intently to the faint signals of spacecraft. As the spacecraft travel farther into space, the ingenuity and foresight of the engineers who designed and built these probes becomes increasingly evident. The longevity and success of the missions can be attributed to an amazing feat of engineering. Designed to last only 5 years, the spacecraft have exceeded their expected lifespan many times over, thanks to redundant systems, robust construction, and the use of radioisotope thermoelectric generators, or RTGs, for power generation. These RTGs convert the heat generated by the decay of plutonium-238 into electricity that fuels the spacecraft's instruments and communication systems. As RTG power decreases, mission controllers are faced with making difficult decisions about which instruments should continue to operate. This careful management of dwindling resources ensures that the most important science instruments remain operational for as long as possible, continuing to collect invaluable data at the frontiers of space. Looking ahead, we expect the Voyagers to continue their silent journey long after their last instruments have fallen silent. Driven by the momentum of their initial launch and gravitational support, they'll drift as emissaries of Earth, perhaps for billions of years. The idea that these spacecraft may one day be the only remaining evidence of humanity's existence, taking the golden records into the cosmic ocean, has its poetic note. The final frontier for Voyager is marked not by a physical boundary, but by our ability to communicate across vast cosmic distances. But even as spacecraft fade into silence, their legacy lives on, a testament to human curiosity and the unquenchable desire to explore the unknown. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the 9th planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh ratio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a 9th planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory, in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Pallidie, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New Horizons' leap into the unknown bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Pallidie is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plane that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, churning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the Sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the 9th planet, has found its relatives among the vast number of Kuiper Belt objects, or KBOS, like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies. Each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kuiper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Arrokoth resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arakoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Wenu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the 9th planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe. In the vast, silent expanse of our solar system, beyond the familiar brilliance of Neptune, rumors of some unseen presence have been stirring astronomers for quite a few years now. This mysterious force, unseen but undeniable, stretches the very fabric of our cosmic neighborhood, bending the paths of distant objects with its invisible grip. Here in the shadowy depths of space, where the warmth of the sun barely reaches, lies a mystery that's baffled the brightest minds. The hypothetical world known only as Planet 9, whose existence can be determined not by direct observation, but only by the subtle interaction of trans-Neptunian objects performing complex orbital motion. Could there be a rogue planet, shrouded in the darkness of space, exerting its influence from afar? A world that defies our understanding and challenges the very limits of what we know about our solar system. Join us as we piece together clues scattered in the back of the solar system in search of a planet that has so far eluded our sight. In the early 1990s, the outer reaches of our solar system began to reveal their secrets. Astronomers discovered a region teeming with icy bodies, now known as the Kuiper Belt. This discovery marked the beginning of a new chapter in our cosmic journey, expanding our understanding of the boundaries of the solar system. Among these distant wanderers was Pluto, long considered the ninth planet and proudly bearing that title since its discovery in 1930. But as the Kuiper Belt uncovered its treasures, Pluto's status began to be questioned. The discovery of objects such as Eris, that rivaled and even surpassed Pluto in size, sparked a debate that shook the foundations of planetary classification. In 2006, the International Astronomical Union was faced with an unresolved situation. What defines a planet? The answer to this question led to a controversial decision that downgraded Pluto to a dwarf planet. This decision, met with both approval and opposition, has swept through the astronomical community and the public, redefining the way we think about the solar system. In this cosmic controversy, however, the seeds of a new mystery were sown: the peculiar orbits of some Kuiper Belt objects, including the then distant newly discovered Sedna, hinted at an invisible influence from the shadows guiding these icy bodies. Could it be that another planet, hidden in the vastness of space, created the architecture of the outer solar system? This question ignited the imagination of astronomers like Mike Brown and Konstantin Batygin, who set out to find the truth. Their journey will lead them to speculate on the existence of Planet 9, a hypothetical world hiding behind Neptune, whose presence is signaled only by the interaction of the most distant members of the Kuiper Belt. A new planet emerging from the heart of controversy awaits discovery. As we move beyond the familiar boundaries of the inner solar system, a realm of icy bodies and distant orbits opens up before us. Here, in the cold, dark regions beyond Neptune, lies an enigma that has captivated astronomers for years. It's the Kuiper Belt, a vast ring of debris left over from the formation of the solar system. Among these celestial wanderers, a separate group shows peculiar behavior that contradicts the expected norms of orbital mechanics. These are detached TNOs, or trans-Neptunian objects, whose paths are free of Neptune's gravitational influence, and extreme trans-Neptunian objects, or ETNOs, whose orbits are so eccentric that they seem to be tethered to some invisible force. What could be the architect of this unusual behavior? The answer may lie in the gravitational anomalies that pervade this distant region. These anomalies, subtle but deep, indicate the presence of a massive object whose gravitational pull shapes the orbits of these distant objects. The detached TNOs, whose orbits seem to be unaffected by Neptune, hint at a disturbance in the gravitational harmony of the outer solar system. Meanwhile, ETNOs, with their extreme orbits, paint a picture of cosmic interaction guided by a hidden force. The quest to understand these gravitational mysteries led researchers to hypothesize the existence of Planet 9, a hypothetical world whose mass and orbit could explain these anomalies. By carefully mapping the orbits of these mysterious objects, scientists began piecing together the potential location and characteristics of this invisible planet. In the tranquil balance of our solar system, each planet plays its part, revolving around the sun in a centuries and centuries and centuries old rhythm. But beyond this familiar rhythm looms a shadowy figure, a silent participant whose presence is felt but not seen. Let's take a closer look at the Planet 9 hypothesis itself. In 2014, astronomers Chad Trujillo and Scott S. Shepard noted an intriguing similarity between the orbits of Sedna, 2012 VP-113, and several other etnos, a phenomenon too unusual to be a mere coincidence. Trujillo and Shepard made a bold suggestion: the existence of an unknown planet whose orbit is a perfect circle between 200 and 300 astronomical units from the Sun. A few years later, in 2016, Mike Brown and Konstantin Batygin embarked on an intellectual journey delving into the mysteries of the outer solar system in order to develop this hypothesis. Through careful analysis and computational modeling, Brown and Batygin pieced together previously found gravitational anomalies that indicated the existence of a massive invisible planet. This hypothetical world, in their opinion, could be the key to unraveling the special dynamics of the outer part of the solar system. As their research progressed, so did their understanding of the potential characteristics of Planet 9. Its mass was originally thought to be 10 times that of Earth, but further research revealed that its mass was slightly less, but still significant, at about 5 or 6 Earth masses. This revision painted a picture of a planet powerful enough to control the orbits of distant objects, yet elusive enough to remain hidden from our most powerful telescopes. The influence of this hypothetical planet extends far beyond its immediate vicinity. Its gravitational influence can explain the clustering of the orbits of detached TNOs and the extreme trajectories of etnos, weaving together a complex picture of celestial mechanics. The hypothesis of Planet 9 sparked a flurry of scientific research, and astronomers around the world joined the hunt for this elusive neighbor. The search for Planet 9 is a journey fraught with difficulty, a testament to both the vastness of the universe and the limitations of our current technological capabilities. Its distant orbit, presumably huge and elliptical, leads it through the farthest reaches of our system. This region, where the light of the sun is almost unattainable, envelops the planet in total darkness. This remoteness poses a serious problem because the potential position of the planet can encompass vast portions of the sky, requiring extensive, focused searches covering these celestial expanses in painstaking detail. It's something akin to trying to find a needle in an astronomical haystack. Moreover, because of its distance from the sun, the planet's surface temperature is extremely low, meaning it emits minimal thermal radiation, making infrared detection just as difficult. The lack of emitted and reflected light is compounded by the glare of distant stars and the myriad cosmic objects that fill the sky, each vying for the attention of our telescopes. Among other difficulties, the nature of the search is compounded by the planet's enormous orbital period, which is thought to be thousands of years. Because the planet's motion across the sky is imperceptibly slow from our earthly perspective. Even after a decade, Planet 9's position in space will have changed only slightly, making any attempt to observe its motion in the short term virtually impossible. This chilling rate of motion means that traditional methods of detecting planets by observing their transit or motion against the background of stars are not feasible. However, in their relentless pursuit, astronomers use an array of sophisticated techniques and instruments, from ground-based telescopes equipped with advanced adaptive optics to space-based observatories that circumvent the Earth's atmospheric distortions. So, in the pursuit of Planet 9, astronomers have had to go beyond traditional observational methods, leading to the development of several innovative approaches aimed at refining the elusive planet's location. They utilize unique aspects of the solar system's external environment and potential celestial interactions that Planet 9 may have with other objects. One of the proposed approaches has to do with potential moons that may orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes internal heat to be released within the moon, potentially making it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid subsurface oceans and also provokes vigorous volcanic activity on Io. This internal heating may cause the moons to emit infrared radiation more perceptively than Planet 9 itself, providing an indirect but promising avenue for detection. Another innovative method involves tracking the trajectories of interstellar asteroids passing through our solar system. These high-speed objects coming from regions outside our solar system could potentially be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational jolts it exerts on passing bodies. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose path through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft passing through the outer solar system can also provide valuable insights. Like asteroids, when spacecraft travel vast distances between planets, their trajectories are slightly and subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unaccounted gravitational anomalies that may hint at the presence of Planet 9. This method requires accumulating huge amounts of data over long periods because the gravitational effects are incredibly subtle. However, the results can be very significant and will pay off the time spent. Moving from direct observation to indirect detection through a planet's influence on its environment may be the key to unlocking one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also spawned many theories and speculations about the true nature of this elusive object. Among the most intriguing are hypotheses that Planet 9 could be a primordial black hole or a dense dark matter clump, each representing a radical departure from the traditional planetary view. The idea that Planet 9 could be a primordial black hole introduces a sharp twist to the narrative. Unlike stellar black holes, formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities may be the size of an asteroid, but have the mass of a planet. The possibility that Planet 9 is one of these ancient, mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this of course does not completely contradict the impossibility of its detection, since such an object would theoretically be no larger than a basketball. According to another theory, Planet 9 may be a concentrated blob of dark matter. This form of matter, which does not emit, absorb, or reflect light, accounts for a significant portion of the total mass of the universe, but remains one of the greatest mysteries. Dark matter clumps, theoretical clusters of dark matter, are thought to have arisen from density fluctuations in the early universe. As the universe expanded and cooled, these gravitational fluctuations led to the formation of dark matter structures ranging from small clumps to massive halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable using conventional telescopic techniques. The primordial black hole and dark matter clot hypotheses emphasize the profound implications of the search for Planet 9 far beyond the discovery of a new member of the solar system. Whether it's an ordinary planet, a primordial black hole, or a dark matter clot, one way or another we'll find ourselves on the favorable side of events. The search for Planet 9 is a testament to humanity's enduring curiosity and relentless pursuit of the unknown. A recent preprint of a research paper by the same Mike Brown and Konstantin Batygin and their colleague Matthew J. Holman entitled Pan-STARRS 1 Search for Planet 9, dated February 1, 2024, reflects the meticulous ongoing efforts to uncover this enigmatic member of our solar system. The study used extensive data from the Pan-STARRS 1 survey, which, with its deep and wide sky coverage, provided a unique vantage point for the search. By focusing on single-night transients and using a sophisticated Keplerian orbit linking algorithm, the researchers sifted through billions of detected objects, a task akin to finding a single grain of sand among the entire North American coastline. This methodological approach represents a significant leap forward, building on the foundation laid by previous surveys, such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 survey, the elusive ninth planet remained out of sight. No features matching the search parameters were found in the data. This result, while not leading to the discovery of a ninth planet, nevertheless narrowed the search area considerably, excluding 78% of the parameter space in which the planet could potentially reside. The remaining 22%, areas with poor observational coverage or inaccessible to current detection capabilities, represent the next frontier in this space search. The journey doesn't end with the PS1 research. The upcoming launch of the Vera C. Rubin Observatory promises to usher in a new era of astronomical observation with capabilities that can finally pierce the veil of mystery, including that which surrounds Planet 9. As we stand on the threshold of these future explorations, the search for Planet 9 remains a beacon of scientific inquiry, a reminder of the vastness of the universe and the small but significant place we occupy in it. Imagine a line, a simple, unbroken line stretching into infinity. This line, in its purest form, represents the first dimension, a realm of length but without depth, a universe infinitely long but impossibly thin. Now, let's broaden our perspective, introduce a second line intersecting the first, and suddenly we're in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a variable alien to them. As we go one step higher, we find ourselves in the familiar embrace of the third dimension. This is where depth comes in, adding volume and substance to our world. Buildings rise, valleys deepen, and the universe takes on texture and shape. But what if we could add another layer? Time is the elusive fourth dimension that permeates our three-dimensional space. Invisible but omnipresent, it dictates the rhythm of our lives, a continuous thread connecting each previous moment with the current one and the current one with the next. In this realm, our understanding of reality becomes more complex and broader. Here, the very fabric of the universe reveals its complexity, hinting at dimensions beyond our sensory perception. However, nature hints at even more complex dimensions. In the field of physics, theories suggest the existence of dimensions beyond our perception, necessary for the fundamental forces that govern the universe. These higher dimensions, although beyond our sensory perception, are crucial to understanding the structure of the cosmos. Join us as we try to unravel their mysteries together today, one dimension at a time. In a historical context, the concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of modern physics. Philosophers once pondered the nature of existence, laying the foundations for our understanding of space. In their discussions, they questioned the very essence of reality, imagining realms beyond the tangible. as the centuries passed, these philosophical speculations paved the way for more structured inquiry into the nature of the universe. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities, but intertwined dimensions that form the fabric of space-time. Albert Einstein, in turn, based on the foundation laid by Minkowski, presented the revolutionary theory of general relativity, restructuring our understanding of gravity, space, and time in a single continuum, forever changing the course of physics. Thus, from the philosophical quest of the ancient thinkers to the scientific revolutions sparked by Minkowski and Einstein, the journey through the evolution of spatial thinking reveals a relentless quest to comprehend the true nature of our universe. So, over time, we've come to realize that to truly comprehend the fabric of our reality, we must go beyond the three tangible dimensions into the realm of the fourth dimension, time. The concept of time as a dimension is both profound and persuasive, defining our existence and the universe as a whole. Unlike the three spatial dimensions, time has a direction. It moves inexorably forward, from the past through the present and into the future. This unidirectional flow of time distinguishes it from space, bringing to the universe a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, consider a simple everyday scenario: organizing a meeting. When we suggest that someone meet at a certain place, we unconsciously navigate the three basic spatial dimensions to determine where. It makes sense that if we arrived at different places, no meeting would take place. However, the when, the dimension without which the meeting will not take place, is no less important. That is, coming with your friend to the same place but at different time intervals, you'll not be able to see each other. This intertwining of space and time is manifested in the concept of world line, the path that an object or person takes through space-time, thus representing its history and future. The idea of world lines provides a vivid illustration of how events are linked together in the fabric of space-time. For two people to meet, their world lines must intersect at a precise point in both space and time. This intersection is not just a spatial coordinate, but a space-time coordinate, the only point in the vast continuum of the universe where both where and when coincide. This principle applies not only to simple encounters but also to the fundamental workings of the cosmos. Celestial bodies from planets to stars trace their own world lines through space-time, their paths determined by the interplay of spatial positions and temporal moments. For example, the Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect on our perception of the universe. It forces us to look beyond static images of space to the dynamic unfolding of events. Time allows us to understand the universe not as a set of individual moments, but as a continuous narrative where cause and effect bind our reality into a coherent whole. The inclusion of time as a dimension has catalyzed major advances in physics, particularly through Einstein's theories of relativity, which we've already mentioned. These theories not only deepened our understanding of the cosmos, but also paved the way for new research in quantum mechanics and cosmology. Einstein's revelation that time is relative, it slows down or shrinks depending on the velocity of an object, challenged the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different reference frames. This phenomenon is confirmed by experiments, for example, with atomic clocks on fast-moving airplanes. In quantum mechanics, time as a dimension underlies the evolution of particle state governed by the Schrödinger equation. This basis is important for understanding phenomena such as entanglement and superposition, where the time dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens the door to a realm where our everyday experience and the laws of physics as we know them are fundamentally challenged and expanded. In search of a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity, physicists have ventured into the theoretical landscape of higher dimensions, where the fabric of the universe becomes even more intricate and mysterious. The fifth dimension and beyond are not just speculative constructs, but important components in the quest for a deeper understanding of the universe. In theories such as string theory, these higher dimensions offer solutions to some of physics' most challenging mysteries, including the unification of fundamental forces and the nature of gravity at quantum scales. The difficulty in visualizing higher dimensions is that our perception is inherently three-dimensional. Therefore, analogies become an invaluable tool. One of the classic analogies to help understand the concept of higher dimensions is to imagine the perspective of a two-dimensional being, often called a flatlander, living in a flat two-dimensional world. This being can move forward and backward, left and right, but has no concept of moving up and down because these dimensions do not exist in its two-dimensional experience. Imagine a three-dimensional sphere passing through this two-dimensional world. To a flatlander, the sphere would first appear as a dot when the sphere is just touching the two-dimensional plane, gradually increasing into a circle as more of the sphere passes through the plane, and then decreasing again to a point as the sphere leaves the plane, before disappearing altogether. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears, without realizing what three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, posits that particles are not the individual points we see them to be, but tiny vibrating strings, whose modes of vibration determine the properties of the particles. This theory requires the existence of more than 4 known dimensions. In fact, it suggests that there may be as many as 10 or 11. These additional dimensions are compacted or convolved so that they are imperceptible on our scale, like the sphere in the flatlander example. In the fifth dimension, we encounter a space containing all possible universes that start from the same initial conditions as our own universe. Imagine a tree, each branch representing a different decision or outcome leading to a different reality, all coming from the same trunk. Just as a person standing at the base of the tree can choose which branch to climb, a being with access to the fifth dimension can explore these alternate realities, each a variation of our own universe, but with slightly different outcomes. The ascent to the sixth dimension opens a plane containing all possible universes with the same initial conditions as ours, but with any possible set of laws of physics. If we think of each universe as a sheet of paper, the sixth dimension would be like a stack of such sheets, each representing a different universe. A being capable of traveling through the sixth dimension could hop between these universes, learning the different outcomes and laws governing each reality. The seventh dimension extends this concept to include universes that start from different initial conditions. To use a library analogy, each book represents a different universe. The seventh dimension encompasses the entire library, offering not just different stories, universes with the same initial conditions as ours but with different outcomes, but completely different genres, universes with different initial conditions. A seven-dimensional being could move through this library, experiencing an infinite number of universes, each with its own unique initial conditions and physical laws. In the 8th dimension, we find a web of all possible universes, each with its own initial conditions and laws of physics, as well as all possible variants of their development in time. Imagine a huge web where each thread represents the timeline of a separate universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The 8th dimension encompasses this entire web, allowing you to travel between any nodes, exploring the connections between different universes and their history. As we approach the 9th dimension, we encounter all possible laws of physics and initial conditions that have existed or will ever exist. This dimension can be compared to the art of origami, where a single piece of paper can be folded into numerous shapes. Each fold represents a change in the initial conditions or laws of the universe. And the 9th dimension includes all possible combinations of folds, resulting in all conceivable and inconceivable universes. A being living in the 9th dimension will not just have absolute freedom to cross the boundaries between all possible realms of reality, it will experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It's the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network, where each branch represents a different outcome or timeline. And all branches ultimately converge at one point, the 10th dimension. Visualizing the 10th dimension is challenging because of its abstract nature. One approach is to use the analogy of a tree, where each branch represents a different timeline or universe, and each leaf represents a possible outcome within that universe. Moving from trunk to leaves, we move from the initial conditions of a universe, lower dimensions, through the various choices and events, higher dimensions, that lead to all possible outcomes. The 10th dimension represents the point where all these possibilities come together, the singularity of infinite potential outcomes. It suggests a cosmos in which all possible outcomes not only can happen, but happen in some timeline or universe in the 10th dimension. The concept itself invites us to reflect on the vastness of possibilities that lie beyond our observable universe. It raises questions about fate, choice, and the underlying structure of the cosmos, prompting a broader exploration of potential realities that may exist beyond our immediate perception. The exploration of higher dimensions beyond our familiar three-dimensional space and fourth-dimensional time has profound implications for both physics and cosmology. Not only is this field of study designed to challenge our fundamental understanding of the universe, but it may also hold the key to uniting the disparate forces of nature, potentially solving some of cosmology's most enigmatic puzzles. Recognizing the existence of higher dimensions plays a key role in the search for a theory of everything, a single framework that will seamlessly unify general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the intricate world of subatomic particles. Higher dimensions may also offer new insights into cosmological mysteries, such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter may be gravitational effects from matter in parallel branches, a concept from M-theory, which suggests multiple parallel membranes, or branes, as fundamental components of the universe, each potentially containing another universe in higher dimensions. Looking to the future in the field of energy, mastering the intricacies of higher dimensions could pave the way to harness forms and mechanisms of energy that we cannot now even imagine, and potentially lead to the creation of clean, virtually inexhaustible sources of energy. Similarly, the field of space travel could be revolutionized by a better understanding of the fabric of space-time, perhaps eventually enabling warp drives or other forms of faster-than-light travel. Concepts that are currently in the realm of science fiction but could be theoretically plausible within higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle gas pedals such as the Large Hadron Collider at CERN, looking for evidence of additional dimensions and the particles that may inhabit them. This experimental work is complemented by theoretical studies that delve physicists and mathematicians into the abstract realms of high-dimensional spaces. As we complete our journey through the dimensions, from the simplicity of a line extending into infinity to the unfathomable complexity of the 10th dimension, we're faced with the inherent challenge of visualizing spaces beyond our three-dimensional experience. Through math, we can describe properties and relationships within higher dimensions, and physics offers theories such as string theory and M theory that hint at the existence of these additional dimensions. Animation such as tesseracts allows us to conceptualize high-dimensional shapes and their projections or shadows in lower dimensions. Further exploration of higher dimensions promises to revolutionize our understanding of the universe. Just as the transition from a flat Earth to a spherical Earth many centuries ago broadened humanity's horizons, this expanded perception has the potential to influence not only science, but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place in it. For years now, there's been a concept that defies the very laws of physics as we know them. A dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction. It's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine. Science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of spacetime. Alcubierre hypothesized that if we could manipulate spacetime in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of spacetime. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter, remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects, or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem: the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery. Imagine a canvas of moments woven with the threads of time, matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomenon. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilyevich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future, or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes, mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort space-time enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explore the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time?